All right. So because I just hit the recording, let me go ahead and just repeat what I just said. So we're going to take a practical look at how the central limit theorem works with a given data set. And we're also going to show kind of some of the limitations of the p-value by essentially demonstrating what p-hacking is. So we're going to take those two tasks, and then I'll do a quick show as to how we covered the concepts in class regarding one sample and two sample t-test. Essentially just to show the relationship between both sets of values. But I'm going to leave that kind of to the latter, because generally I think explaining the p-hacking helps really kind of showcase how the t-distribution works. And the tests themselves, once you know how to code them, then that part's pretty straightforward. All right, so I'm going to share my notebook. We're going to keep it simple today. We're just going to use the Titanic data set. Matt, feel free to interrupt at any point with any questions. Oh, hi, Diana. Give me a second. All right. And yeah, with this notebook, Diana, welcome. Giving you a section. Diana, welcome. Just a quick heads up. We're going to go over a couple of concepts that sort of touch on the more like the conceptual aspects of the statistics we're working with. So we're going to take a look at the central limit theorem and show an example case of how that works and how that potentially fails. And then we're going to take a look at how p-hacking actually plays a part when it comes to using the p-value to kind of identify the statistical relevance. So we are going to keep it simple. We're going to stick to the, for today's review session, we're going to use the Titanic data set because it's something we've seen plenty of before. We know what to expect as far as the answers go. I'm going to source the data set from a different location. So first and foremost, we're going to use 4 packages. We're going to use the pandas package. So the text you would use to read this in is the pandas package, the numpy package, these are your standard go-to, your matplotlib package with pyplot as PLT, and the Seaborn package. So the only one I might not use is pyplot or the matplotlib, because the visualizations for this are going to be focusing a lot on Seaborn specifically. Particularly, I'm going to use the data set from Seaborn. So I'm going to call the data set values. So if you actually use Seaborn, you'll see that you can get a bunch of built-in packages within Seaborn. What I mean by this is that Seaborn itself also comes with a visual library of packages that you can use for demonstration purposes. So the Titanic data set is included as part of this package, and we can include that data set as a means of loading that as our value. So if we take our Titanic value, we can include our Seaborn as a load data set. We're going to use that Titanic value here. We can include it as an object for interpretation. Right, so we're familiar with this. Note that this is a little bit different from what we worked with before. The idea is that you're intentionally using this to kind of add, there's more to explore. There's more different visualizations that you can use as part of this scenario. The other thing to note is that I'm also eventually going to be using the SciPy package, the SciPy packages. So one thing that I do want to make sure that we showcase is that as part of any notebook, you do want to actually specify what packages you're using at the very top of your notebook. Again, this allows you to tell a more clear story from what kind of packages you're working with. Since I'm only using specific functions, let's call from the SciPy stats library, I want to import just these specific packages. We've used the chi-square contingency. We're going to use the t-test, one sample. We're going to use the t-test independence. And we're also going to use the t to measure some intervals. Matt, are we clear on the difference between the one sample and the t-test independent test?
Honestly, not
Cool.
terribly.
Perfect. Want to ask just so that we can kind of explore that a little bit further at the end. Any questions about the load data set business, like how this came to being?
No, that's all pretty
Cool.
straightforward.
All right, pretty straightforward. Cool. All right, so let's skip to the example of the central limit theorem first, or p-hacking and the central limit theorem. So the central limit theorem essentially states one thing, that there are certain patterns, expresses two things. There are certain patterns that we can expect from a normal distribution. The normal distribution is that, where's my drawing tool? Where's my drawing tool? Come on, drawing tool. All right, so if we have these values, we have that bell-shaped curve object. If we have that normal distribution value, we can expect most of our values, our mode, our mean, and our median to be exactly the same value. That's our symmetrical distribution. If you close it like a book, visually speaking, it looks like a book getting closed down. This is a value. A normal distribution refers to like a species heights, so human body temperature, human heights, the amount of, what are other examples that are generally focused on normal distribution? Can't come up with any more examples off the top of my head, my apologies. But like, if you think about it in simplest term, human height or human body temperature, we expect there to be individuals who are generally about an average height. And then there is going to be within any group of people, people who are taller and people who are shorter. But that amount, the amount of people essentially decreases in either direction. There's going to be fewer short people and there's going to be fewer taller people as the scale increases. So we use the normal distribution as a way to kind of measure what is a value that is kind of on the outskirts of the mean median. So for example, if the average human is about, say, this tall, we can expect people who are individually taller, like say someone who is 6'0" to be somewhere above here, which is tall, but it's not, unusual. Something that is unusual would be someone who is 7'8". And we can expect there to be far fewer individuals of that height. And much less expected would be an individual who is 9'7", for example. So someone who's that tall, there might be one or two individuals, but that is such an extreme outlier to our average human height that we don't expect to see many 9-foot tall people. So the normal distribution essentially accounts for the number of individuals that may be, or how the number of individuals would fit within a specific distribution or a specific set of values. Now, because we can think of those 9-foot tall people as outliers or exceptions to this distribution rule, we can expect those individuals to be on the far outskirts of our normal of our distribution value. So that property or that same concept means that we can then consider any value that's on the furthest extreme to be very much unlike the distribution or the general distribution of a normally distributed group of individuals. So you follow that up, that same kind of logic with, that means we can apply certain mathematical concepts. So for example, what is the probability that a 9-foot tall person would be a part of this distribution? The probability is going to be very, very small. Does that logic sort of make sense so far?
Yes.
Yeah. So taking those concepts taking that concept into account, the p-value means that what is the probability you have this 9-foot tall? If it's super small, do we apply certain types of hypothesis testing concepts using this normal distribution? So we take these null and alternative hypotheses as a way to, we fit this into our concept of distribution considerations and determine what is the probability that our value fits into this distribution, and apply that to the way we think about null or alternative hypotheses. Because for different types of distributions, you can make an assertion that the null hypothesis is going to be what is the status quo. The status quo, when working with a normal distribution, is that, well, your values are going to fit within the normal distribution. Now, in that sense, we identify, or we introduced a couple of different types of distributions. One of them was the conditional distribution with Bayes' theorem, and the other one was the T distribution, which is a distribution that works as kind of a sampling value where you take into account a smaller sample size and take those values into consideration. The other component of the central limit theorem states that out of any distribution, if you take enough samples and measure and get the average of those samples, if you get the average of those samples, you can expect to have a normal distribution. Let's take a look at what I mean by this. So if we take a look at our Titanic passenger class, that's P class, is that the name of the data set? No, it's Titanic lowercase, and then P class is lowercase. Here we go. So if you take a look at the Titanic P class, this is the passenger class for all individuals on the Titanic. If you take a histogram of that passenger class, you'll notice something interesting. Do you have a name for this type of distribution?
Is this the right tail?
We haven't actually talked about it. This is actually, yeah, so that's a trick question. We haven't actually talked about this type of distribution. This is not quite a binomial distribution because there aren't a positive or negatives. This is really just a bar chart. So that's a trick question on my part, my apologies. All this is showing is that for every passenger class, we have this number of individuals. The distribution doesn't really skew one way or the other. There's like more individuals in the third passenger class with the fewest individuals in the second passenger class. The distribution doesn't really fit a normal pattern necessarily. You could say it skews towards the third passenger class. So it skews towards the lower class. But I don't exactly remember the name for a three. This really works as a bar graph. But it's still a distribution, and the central limit theorem still applies in the sense that if I take enough samples from these three groups, I can create a normal distribution. So let me show you what I mean by this. If I take a sample, and I'm going to do this step by step. I take a sample. This dot sample essentially takes a sample of values from essentially a random sample. If you create this as a histogram, whoops, that was a typo. I make this into a histogram. This is going to look very similar because essentially all I've taken is, let me take 50 rows or 50 samples and throw them into a bar graph. It does exactly the same thing, right?
Mm-hmm.
But if I were to take 50 of these samples and if I were to take many samples of this, so say I want to do multiple samples. So this is my first sample. So this is one sample. Oops. Ooh. Oh, copy, paste. This is my second sample. So that's two different samples that we can demonstrate. So we can do this for a bunch of different samples. You'll see that this is a second sample, but it's different. It sort of looks the same thing. Let's say I want to take 30 samples. In order to do that, what I'm going to do is I'm going to take a for loop where I essentially take 50 samples. So for I'm going to use the range values so that my iteration occurs 50 times. So the same thing I just did where I did first, second, third, what I'm going to do is that my first value for 50 iterations, I'm going to have a value for I assigned a specific sample. as part of this process, what I'm going to take is include these all as sample means. And the sample means will all be added to this list of values. So sample means will append my values for I. And within that I, what I want is the mean of those samples. So I'm just going to attach that I want the mean for those samples. Let's go ahead and run that. Let me just make sure that this looks appropriate. I'm going to run twice. So if I take my sample means, these are all of the averages of all of the samples that I've taken from this value. So if I take a histogram of those sample means, it's not going to work because it is not a pandas object. So instead, I'm going to use the Seaborn distribution plot, which is pretty much the same as the histogram, and run a distribution of those values. Note that the original data set is 3 specific graphs, but when you include more samples or when you take more samples, it starts to look a little bit more like a normal distribution. And if you change the number of values, say to 100, note that this is a different range of samples. It still looks a little bit right skewed. Let's increase our values. It begins to look more and more like a normal distribution. And this is essentially a fundamental rule or a fundamental theory of statistics, where if you continue to take larger and larger samples from your values, you can expect, or an increasing number of samples, you can expect your distributions to increase, your results to look more like a normal distribution.
It's interesting.
Yeah. And this is just a matter of like taking, and this is an important part, you're taking the means of the sample means. So you take a bunch of samples, you take their averages, and then you calculate what those averages look like. So it's kind of the average of the average. Or the distribution of the averages.
In a real world example of, if you have something from your restaurant experience, I understand this is explaining the central limit theorem, but when would this, because in this situation, we're looking at 3 classes, 1, 2, and 3, and obviously the averages or the means are breaking it down into decimals, right? So we're obviously on this x-axis not seeing 1, 2, and 3 any longer. We're seeing the decimal, right? So in what way in a real world situation would we be doing something like this, I suppose? So
there's a couple of instances where you see this same concept apply in a real world scenario. So for example, think about how your bank account flags you when you're seeing a fraudulent activity. Generally, a fraudulent activity is based off of, it looks at where there's a number of features that get taken into consideration. But one of the considerations it takes into account is that it looks at especially in the early days, it takes a look at your spending patterns and detects those patterns. What it looks for is any outliers in your credit card purchasing. So if something looks unusual, or if something seems to pop up where the probability of this purchase may potentially be different from what you would normally purchase, essentially it gets flagged as being an outlier purchase. Outliers measuring that this is a purchase that was smaller, or generally speaking, larger from what you would normally buy. You apply that same rule to a regional area or a regional distribution, you can expect to see those you can expect to have software that flags any type of purchase that doesn't really fit. As far as restaurants, as far as restaurants go, the value of having an understanding like this is, say you have a restaurant with 5 tables. Let's say you've got these 2 tables. Let's say these 2 tables are, let's say this is the window and these are our tables by the window. This is a corner table. And sadly, this is a real world example. This is a table by the bathroom. So without having to do any statistics, we already know which tables are probably nicest for any given scenario. You can essentially expect that, you know, your tables by the window are going to be pretty well populated for people who want to sit. You want to expect the corner table to have a different kind of vibe, and you can very much expect that the bathroom table is a table that never gets sat. The account you can do is begin to consider what the sales histories is at every individual table. So for example, if you can take into consideration all of the purchases that happen at each one of these tables, you can begin to create a distribution of different tables. So for example, if you've got this type of distribution for every single table. So what I'm doing here is you take the purchase history for every customer who's ever sat at this table, these 2 tables by the window, and you essentially measure this on a distribution scale. You can expect there to be a normal distribution after you've taken enough sales data for the Windows table. And then you take the history of this table and you begin to measure the distribution. In this scenario, you've begun to get a study where you're not just looking at the average sales for every single table. That part is pretty straightforward. You now, by developing a normal distribution or developing some type of distribution assessment for the purchase history for all of these individual tables, you can begin to recognize when or what happens when someone who sits at the bathroom table just ends up happening to order on the outskirts of your normal distribution. So now you've been able to identify, hey, one of these days, someone sat at the bathroom table and ended up spending way more money. Let's find out. Let me be the manager and just go over to that table and be like, hey, you seem to have had a really good time and spent a lot of money. 1, why? What kind of assessments could you deliver from that experience? Why did you enjoy the bathroom table so much? Because then you can essentially create a new distribution for improving the scenario on the table based off of the feedback of that one individual.
Okay,
So
cool.
yeah,
Definitely makes more sense.
Yeah. So it's things that are kind of logical if you think about it but when you apply statistics, you can actually quantify what's the amount of money that a person needs to spend at the bathroom table for it to be unusual, or hey, someone spent an unusual amount of money at the bathroom table. All right, so let's take a look at one of the caveats to the normal distribution when you're thinking about how this works in terms of the probability value. So this is a little bit of a longer bit of code. Okay, I'm going to put a pin in that, because from here, let's just go ahead and follow up what I was saying with regards to the bathroom table. Let's take a look at the one sample t-test here. So before we go into the p-hacking concept. So the one sample t-test, in other words, the, what was it called? This is t-test one sample. The t-test one sample works under a very specific set of presumptions. So this is a t distribution where, understanding all of the rules that we've applied to this normal distribution, we need to determine whether using a sample of a set of values can be interpreted to be part of this normal distribution. So in class, one of the things we did was we took the average age of individuals on the Titanic and tried to measure whether that average age, so if we take the mean of the average age, we determine this value to be close to 30. What the t distribution does is that it sets up a normal distribution that essentially tends to be a little bit more flexible. And it draws a line. And with that one sample, you need to include a reference value. In class, we essentially talked about like how you use this in terms for Coke products, where the reference value was something like 34 or whatever. In this case, let's say that we have a known value where the age of people traveling across the Atlantic is said to be 30. What this does is that it essentially throws a normal distribution with your 30 as your mean or your median value, or a t distribution. Again, a t distribution looks very close, very similar to a normal distribution. And then measures whether your series of values, whether your array, actually fits within this normal distribution. It tells you what is the probability that this average age is lined up with this reference value that you're working with. So the function itself requires you to take your sample, and again, this is a one sample t-test, and link it to your values for your reference value. And actually, this is so very close, it didn't quite work. Let me see if I change this up a little bit. Am I doing something wrong here? Why are we not? What's not working? T-test, yeah, one sample. That's weird. So if the fair was that, what is this, 30? Okay, so that works. Why does age not work? Let's take a look at what's going on with age here. Count 714. Titanic shape. Aha, okay. I've got some null values that are throwing everything out for a loop. Okay, so let's adjust our data set here for a second. So what was happening? How did you determine what the difference was? Well, my count of values says that there's 714, but there should be 891 rows. So let's just go ahead and drop my null values. In place equals true. And take a look, see just how much damage we've done to our data set. I did a lot of damage to my data set. Great. Let's do something a little bit different. What I'm going to do.
Doing that. Do you mind refreshing my memory on in place equals true?
Of course. Okay, sorry. Yes, good catch there. So what just happened? So I dropped a bunch of rows, but I dropped every single row that might have potentially had a null value inside my Titanic data set. I went back and I reread in my data set just to be able to continue onwards. In place true specifically just makes a permanent change to your data set. So if I've got a Titanic data set and I include my pandas function for drop num, this will return a data set with 182 rows. In other words, all of the values that might have been dropped from the data set. That where like any row had no values, yeah. However,
that will just drop it from the origin.
Yes. However, just by dropping or just by showing the values doesn't mean that the change happens to my Titanic data frame object.
I see.
Yeah. So the confusion comes from the base pandas. Say, for example, if you have a list of values like 1, 2, 3, and 4, generally speaking, the classes in the functions inside base Python objects make changes permanent. So you'll see that this object pops out. Let me actually just let me be a little bit more clear about this. Test. So if I test pop my values, it'll pop up my values for 4. But the change happens permanently.
Right.
Yeah, pandas is different in that you have to be explicit about the fact that you want to make the change with a pandas function. So you can, so you can either do Titanic, drop na. That will drop all of your missing values. I'm going to specify that I want to drop my age values. We're going to call this Titanic age. So what I'm doing here is I'm just using the features or the function. I just want to create a list of values based off of the Titanic age column and drop those columns without dropping everything else from the data frame. So if my Titanic age value, so I can either drop those values individually, or I can make a change to say, for example, Titanic, what is it? Fair. Let me just make sure that this has null values. There are no values here. Let's say Bart. I think that one has a bunch of, so there are 2 null values in this data set. If I wanted to drop those 2 null values, I can do those changes in place. I cannot do both steps, or I should not do both steps, because the in place creates the drop not into a function value. And that function value is by default a none type object. So if I take a look at my Titanic age value, if I take a look at my Titanic data set now, I should be short. What was my original shape of the data set? Yeah, so the data set still has 891 rows. Okay, questions so far?
Okay, that helps.
Okay, so let's take a look at the t-test now that we don't have missing values. So now that our t-test for one sample, we're going to use that Titanic age value, understanding that this is a function that requires both the array you're working with or the list that you're working with and a reference value. We now get an interesting result, because what Titanic age tells me, if I take a look at the mean, is that the number 29.69 is actually although it's very close to this reference value, the p-value of 0.58 means that in a normal distribution, say for example, let's say this is our normal distribution. The value of 29.9 has a 58% probability of being super close to these values. And I can tell that because the t-statistic of negative 0.55 would suggest that the distance of 0.2969 to the value of 30 is actually really close. No, what I'm measuring is where this value pops up in my t distribution. If it's close to my mean, median, or mode or of the t distribution, it means that it has a very high probability of being part of this same distribution. It's not an outlier, it doesn't exist on the fringes. However, say if our reference value was something like 35. Note that my value for 35 is now extremely different from 29.69. When you run it, this p-value number got really small, suggesting that the probability of this value is going to be, and the distance, see that this is 0.97, it's a larger number, means that the distance is so far off to the left that the probability of it being part of that same distribution, where your t distribution of 30 fits into the distribution, is unlikely to happen. Which suggests that we can, given a null hypothesis and a significance level of 0.05, remember, the significance level, all that's measuring is where in the normal distribution are you setting off your cutoff point. Does that part make sense?
Yes.
Okay.
And that would be typically 0.025 on either side.
Correct. Exactly. In a two-tailed distribution, which is most of what we're working with, what you can expect. Now note, this is very specific and it's very like the sample size that you're working with is going to very much play a part in the equation for a t distribution. So you don't necessarily need to have you don't necessarily need to know the math behind it, but it's helpful to understand that this reference value is the drawing of the t distribution value that you're creating. If you were, for example, to take the same concept, say your t-test, one sample, fill it out. No? Okay, we don't want to fill it out. All right. And say that I want to take a sample of these values. So take note, I'm taking a sample of 30 values from this distribution. So what I'm taking is my Titanic age, and I'm taking a sample of those values and say that I want to measure them against the mean. What the t-test one sample helps you determine is it likely that the sample that you've taken, when measured against the reference value, is it possible that this sample is a part of this population? And the result is, with a t-statistic of 1.09, note that we're working with a smaller sample, your p-value suggests that this particular sample might, you essentially fail to reject the null hypothesis that your sample is a part of this distribution. It essentially means that this sample, given this p-value, is indeed a part of this distribution. Sorry, I might have gotten myself mixed up there in my explanation. What this tells me is that the sample of 30, which we understand, it's a sample of this average, fits. Note, if I take a different sample, my p-value, it's still a part of the distribution, will continue to suggest that the value is a part of that distribution. If I do this again, you'll get a different results. All of them are above your significance level of 0.05. And as a matter of fact, because you're working with a significance level of 0.05, it is more likely than not going to continue to work this way. So I'm going to go ahead and grab this, and I'm going to share this on Slack so that you can use it. Let me make a slight change here, because instead of Plotly, I want to use Seaborn. And working with the Titanic data set, let me just go ahead and make this easy change for me. Titanic is equal to Titanic. All right, so you'll need both of these sets for this code to work. This is a playful one. Titanic, and then this code has been adjusted. Yeah. Okay. So now with this, what I'm running is 20 instances of this specific test, where I take my sample value from the group itself, measure it against the average age of the Titanic distribution. Age is lowercase. That's the other error for age. Is age. Stats is not defined. I read this in as a different package. Where is the stats package for this?
In the center there, under the print statements.
Import from SciPy import stats. Ugh. This is why consistency in your code is important. Seaborn has no attribute histogram. Nope, you're absolutely right, because it is a displot. I will share the correct code. There we go. Oh, it didn't actually work. Perfect. Cool. All right. So it's working a little bit less effectively than I'd like.
Kind of a topic, but
yeah.
How often, when we were discussing commenting through the code to have anyone else that comes in and looks at your code kind of be able to know what's going on, how often are you really doing that?
I'm doing it very badly. I'm very bad at this. I will absolutely recognize that commenting is not one of my strong suits. However, you should be doing it as often as possible. This is very much going to be one of those do as I say, not as I do, but the more you comment in your code, the better. Most of it, the problem comes from a place where I am consistently talking about the code that I'm writing. So it's intended to be recording, but one of the habits that I do want to implement is, yeah, as much as you can comment, the better.
Okay.
Yeah. I'm going to, because this isn't showing this the way I would like to, I'm going to simply show this in a different notebook that I have for just a moment, because I'll just reflect this a little bit more clearly. All right. So you should be able to see on this notebook.
Yep.
So here we go. So the difference is with using Plotly, the different packages, note that this same result is exactly the same result from what we were seeing earlier. The p-value for the distributions, where you take a sample from a given value, all seem to line up with saying this sample does fit as part of the distribution. At the end of the code block, I actually share any instance where the p-value did not suggest that your representation was part of the distribution. So here you see that there's a p-value of below 0.05. The idea being that this is one of those, this is the only instance where the sample was very much on the outlier of the distribution itself, of the t-distribution. And that's because any given sample, if you just happen to take a bunch of values on the extreme side of a distribution, you can expect there to be a 0.05% chance that you got an extreme set of that samples, so that their average, when measured against the t-distribution, is on the outlier side. And the p-value will indicate something like this happening 5% of the time. So note, if I run this code again, it tells me I ran 20 tests. Out of those 20 tests, most of the time, I get one result that says you reject the null hypothesis. But given the fact that this was a 1 in 20 chance, let's take a look at our 1 in 20. This is a reject null hypothesis, where my p-value is indeed less than 0.05. I just happened to get lucky that the samples that I took happened to be on the extreme side. And in every instance, when you're working with p-values, there's always going to be a 5% probability that you're going to have this happen as a matter of course. Does this make sense?
Yes. So in your restaurant example, you could then tell the owner that after running these tests, there is, to just use the same numbers, a 5% chance that the bathroom table will provide a high bill based off the statistical data that we.
Correct. And we can expect that if we've got that distribution, we have a measurement for what that high bill might be. Because then that measurement is, if a table comes in, sits at the bathroom table, ends up spending more than that cutoff point, you notice that that is something that didn't just happen. This either didn't happen by chance or that there's an improbable situation happening. And you've got a guest who just ended up spending more money at that table for whatever reasons. So then the question is, what do you do with that information? Because now you've got that one individual in your restaurant. Do you go up to them and ask them like, hey, what is it about the bathroom table that you like? Because that was an outlier experience.
Right.
Okay. Let me go back to the notebook itself. Let's share another example of this here. Where what I'm going to do is this. The next step is understanding how the two-tailed distribution works, or the two-test distribution works. So in a similar vein, whereas the one sample distribution is essentially one t distribution, a two-tailed distribution, or a two independent sample distribution, is essentially two sets of t distributions. And then the question is, are these two distributions very different? Like, are they two completely separate distributions? Or are they distributions that are similar enough that they could technically fall within the same population distribution?
So for example, window table versus corner table.
Correct.
Are they close enough that the everything aligns? You could spend.
Correct.
Or you could make business decisions based off of either table because of their alignment being close enough.
Correct. So it's a matter of trying to determine whether the two distributions are alike enough to work within the same line. In class, we did our Titanic males. We're going to go ahead and identify our male. Do we have that as a, how does it pop up in this data set? Titanic. Let's take a look. Okay. Ugh, I use gender here. All right, so that's my first value. Simply going to have these be two different data sets. So one is for the men, the other is for the women. And we've got two different values here. From this value set, one of the things we recognize is, we remember from class that the distribution of people in the Titanic, say if you've got a seaborne displot, where you take a look at their age distributions, is different for one group as it was for women in the group. See how it lines up side by side. I think I did this in class where it was actually overlapping one over the other. Let's see if I can do that really quickly. PLT histogram, PLT histogram. Yeah, all right, so we've got both sets of distributions. The question ends up being whether the distribution of these sets of values potentially fit together. We can actually see that kind of already in place based off of like how these values work. But if we were to take our two sample distribution, you can already see the results where the age of individuals who are male on the Titanic against the individuals who are female on the Titanic. So the t-test independence, so I've got null values to consider here. Let's go ahead and just drop those values above. Okay, 6, drop, nah. This is not clean. This is not very clean code. I broke something here. What did I break? Okay, so that still works. Let's do this as a drop now value. Let's add the drop now down here. Cool. All right. Note that the t-test distribution, when it's essentially measured against each other, they won't work when there are null values in your distributions. But note, the p-value suggests, hey, these two distributions didn't happen by chance. We can reject the null hypothesis that there's a difference. We see that they kind of fit in the same pattern, but note how many more male individuals there are on the Titanic for this scenario. So the distributions on individuals' ages seems to suggest that there is a significant difference in the male passengers. And we can sort of see that from this distribution where there are some male passengers. For one, there are more male passengers in this group, and they skew on the older side. Whereas female passengers, although they seem to share similar distribution, they're not exactly the same. They wouldn't exactly be considered part of that same set of they're not within the same category. There's a significant difference between the age of the men on the Titanic and the age of the women on the Titanic. And the p-value seems to suggest that this didn't just happen by chance. This is something we could expect to see based off of those distributions. So the logic behind it is, although we can see that the distribution of people seems to be the same, there seems to be somewhat of a different population happening here. And based off of your t statistic being a little bit higher, 2.49, it seems to suggest that one of these individuals skews a little bit older. So again,
and the t statistic is measuring
just the distance between one value and the other. Yeah.
Okay.
So if you were to like invert this, so take this for one side, I think this is an absolute value, so it measures the same thing. Whoops. Take that out, put that there. Let's see. Ah, yes, see, it turns negative when you invert the values. P-value stays the same, but it's just now pointing in a separate direction.
Interesting. Okay.
Okay. The last one we'll take a look at is the chi-square contingency, because the same rules apply in this case. The chi-square contingency is essentially just using categorical values and the frequency of those values to determine whether there's a relationship between two different categorical values. So for example, what we did in class is we looked at the survival rate to the passenger class, to the, what other ones can we use for an example here? Let's see if there is, let's see if people from a specific town survived more likely than not. Let's see if embark town. Let me see what this looks like as a value counts. I just want to study this before I dive in here. All right, so we only have 3 categories. That's perfect. So if we take a if we take a look at the relationship between individuals from a specific town for those who survived, we need to create a joint distribution. That joint distribution can be created using the pandas crosstab, where we measure the values that we want on our index. In this case, I want embark town. Embark town. And I want that to be my from my Titanic data frame. So this is my one value. Titanic, whether they survived or not. Index, columns. There we go. So what this tells me is that for the breakdown of the individuals from the different towns, which ones survived, which ones didn't. Obviously, we have very different, this doesn't take into account the percentage class, but of those who survived, there's a question as to how many of them, like whether there was an actual rate of survival, because there's a couple of things we can use for measuring what an expected value is. We won't necessarily go into the math behind it, but the chi-square test, what it tells us is that based off of a contingency table, or this joint distribution table that we've created above, is there a relationship between a specific that, like, are these variables truly independent? Or is there a statistic probability that these values are different from what we would expect the frequency values to look like? So when you run this chi-square contingency table on its own, it tells you a couple of things. One, it tells you the chi-square statistic. Second, it tells you the p-value. The p-value aims to say, so that p-value is your second value here. Just return that as an object. Seems to say that these values are actually significantly different from what your expected values would be. Because if you take a look at the expected values, I'm going to return them as a data frame. We can see that our values, had the null hypothesis been true, where the values of where someone embarked from and whether they survived are both independent features, there you can expect these values to look something like this. This is one of those things that the chi-square contingency table returns as one of its output. It returns the expected values if indeed the null hypothesis is true. And the calculation for the expected value is, it's essentially a calculation given the average of the distributions. We look at the margins of those values, calculate them against the margins specifically. The math is unnecessary. You just want to, like, the math is fun to do on paper, but it's not super important to know. What you need to know is that the chi-square contingency tells you if indeed there's no relationship between survival and your embarked town, this is what you expect your results to look like. But your actual results look a little bit different. There's a significant difference, for example, in Cherbourg, where 93 people survived, whereas if we were actually working off of expected values, where the values don't actually make a difference to each other, this is what we would expect to see. And that chi-square contingency tells you just how different these values are. This p-value, being so small, suggests that these differences didn't just occur by chance. There is indeed some type of active effort occurring between these two variables, survival rate and their embark town. It might not be present in the individuals from Queenstown, and perhaps less so in the Southampton, but clearly the folks from Cherbourg might have, or at least 30 individuals from Cherbourg might have actually lined up to work with each other.
So the expectancy, how is that being calculated? How are those numbers?
Okay.
What is it basing it off of to get an expected?
So I will share with you a kind of step-by-step process from these guys, because one, they explain it a lot better than I do. But what you need to know for this to work is that it's simply a matter of calculating calculating against the total of those values. The kind of math you would do is to break this down. Where is it? There it is. So you're essentially breaking down your values based off of how many features you're working with. And you take those values on a discrete level. So it breaks them down into categories and essentially returns the average between those three categories. So do you remember how we did let me show you. Do you remember how we would measure both the margins from our, say, so if you take the crosstab, you remember how you take the margins of those values, or the margins equals true, and then we followed it up with the normalize equals index. You're essentially creating an average based off of the amounts you're getting from all three sets of your values, breaking those down on a scale by scale, on a level by level. And then if you're expecting there to be an expected amount, I think it breaks these down into the pattern they see from both sets of averages. So it determines what is the probability of these averages occurring. It looks at the majority values and essentially returns what those values might look like. The calculation itself is a little bit more kind of breaks this down one step at a time. And it's worth reading to actually getting the kind of the math behind the scenes, but it's essentially a row by row calculation based off of a calculated average.
Gotcha. So it's just looking at those numbers and saying, based off of the math the system has run, this is what would be expected based off of that mathematical probability.
Yeah. So the video itself is the formula itself is just kind of it just, you expect to get for example, this is the example that I like to refer to, where if you are kind of randomly answering a multiple choice question with 4 answers, you can expect to get 25% right by just being the probability of getting those values. So in this case, yeah. So it goes a little bit deeper because based off of how many rows you're working with, you might expect there to be a different, the degree of freedom is part of that calculation for the probability and measuring that distribution. But rather than having to pull out big charts, like for example, the chi-square contingency chart, no, that's not what I'm looking for. I'm looking for the degree of freedom chart. That's what I'm looking for. The contingency charts for this are values that kind of look like this, where you take a look at the distribution of those values and you need to come up with a specific value. So that contingency analysis is outside of the scope of the class. And frankly, I've avoided using these distributions because in the end, it always ends up being 0.5 and these values tend to be your standard. Yeah. Mostly when I use this, it's typically to just kind of indicate just how different a specific result would look like. I don't think I've had to use contingency tables as a scale on in a professional capacity, but understanding this type of normalization helps us understand just how conditional distributions essentially work with. Because what this helps build into is how the Bayes theorem essentially calculate, or the conditional distribution value calculates a specific value when you have, for example, whether an individual survive, given that they're from Sherberg, is essentially why you would use a distribution table like this.
All right.
Yeah.
Essentially, the One sample t-test is just using the one distribution. Is it an independent t-test? Is that what it was called?
Yes, correct.
Is comparing two distributions to see the relation between the two.
Mhm.
And the chi-square test is using essentially almost like an X and Y of two different categorical values to determine relation.
Exactly. That's really it. Bayes' theorem is essentially building off of your conditional distribution to come up with a specific equation. The philosophy for Bayes' theorem is that in a lot of ways, you rely a lot more on your prior belief of a specific probability occurring. And that after your prior belief has been found true or false, you can determine, or once you've determined whether that prior belief is accepted or rejected one way or another, you can apply that prior belief to, you can apply that prior to your posterior belief, and that posterior belief then becomes your prior within a new calculation.
Yeah.
So let me see if I can find a quick example here. That's not what I'm looking for. It's not quite what I'm looking for here. That was 1.24.
Kind of off topic, but
Yeah.
got you at least. From your experience, would you say that jobs existing in the data science field are more suited for employee type of positions, or do you see possibility or opportunity for more freelance
Both.
positions?
I did freelance work after, so I did. Let me go ahead and just pause the recording because I'm out of time. Okay.